Couple things to point out. Yesterday's lecture video is right here, so Gibbs free energy. Kind of click on it, watch the video. You definitely want to watch it because it's going to show you how to do some of the free response questions that you're going to have as part of your homework assignment. But what I want you to do right now is you're going to click on this MCFRQ, Spontaneity, and Gibbs free energy worksheet. So just click on it. And it's something that looks like the following here. So what we are going to do is we are going to look at some of the problems that we have sitting right here. So I'm going to go here. And we're just going to kind of work through it. So these are going to be problems that you're going to have as a part of your homework. But we're going to do some of the problems together just to kind of show you that even though you have, I think it's like maybe 35 of these multiple choice, you're going to zoom through some of these really quickly. So for instance, number one, it says, which of the following representation shows a process in which the entropy of the system is decreasing? And I think we looked at this one yesterday or the day before, and we said that the one that shows the entropy is going to decrease is going to be what? D. So D is clearly, we can see that it's coming together and it's more organized in that case. So the entropy in this case would be a delta S, which would be a negative value in this case since we see the entropy decreasing. For the next problem, let's see, can we do this one? Yes, we can. What I want you to do is I want you to take this problem. If you look at it, they're showing us the actual reaction that's playing out here. And they're giving us, in this case, our S's. So they're giving us our entropy. And they want you to figure out, hey, what is going to be the S for the overall reaction? So you're going to go in and you're going to solve this problem. And if you remember, the way that we can solve this problem is we solve it just like what sort of problem? Exactly, like the delta H formation sort of problem, where it's, hey, products minus reactants. Remember, even up here, this is given to you on the equation sheet. So when you take that AP exam in May, it's showing you right there, hey, products minus reactants, delta H formation, products minus reactants, delta Gibbs, products minus reactants. So what I want you to do is just go in there really quickly and calculate this. And keep in mind, if this is like a multiple choice question that's actually on the exam, you don't want to sit there and waste a whole bunch of time here. They're not grading you based upon, oh, you showed all your units. For a response, athletes, show as much as you possibly can. But for a problem like this, if I was to go in and solve this on an actual AP, I would go in and say, okay, well, I know my delta S, products minus reactants, well, I got 2 times 330 going right here. I'm going to go in here and say minus, and I'm going to go in here and say, okay, what do I got for products here? I've got, in this case, 2 moles of this, so 2 moles, and there I am moles there. I'm going to go 2 times 310, plus I'm going to go with, hey, that's 1 times, in this case, 210. I'm going to put this in my calculator and get what the answer is going to be really quickly. Now, once again, FRQ, different story. I'm putting moles here. I'm putting the actual units that are going right there as well. But for this one, I'm just going through it really quickly. And if we solve it, what do we get for this one? It's negative what? 170. Okay. And there we go.
Did you just mentally do that? Yeah.
I'll see, that's 990, isn't it? That's going to be 620 plus the, let's see, minus 620 minus 210. Yeah, it's going to put us closest to right there. All right, questions over this. So only thing I'm trying to show you is that some of these problems are going to go very quickly. Like for the next problem. For this problem. And I know it's kind of hard, especially if you're trying to watch this as a recording, but once again, you have it right there. Kind of look at it. Basically what they tell us for this particular problem is they tell us that, what we got going on here? It says the decomposition reaction of hydrogen peroxide is represented by the equation above. A student monitors the decomposition reaction at a temperature of 300 kelvins and records the concentration of the H2O2 as a function of time. The results are given below. Which of the following is going to be the delta G and also delta S for this process? Well, if I look at it, one of the things that they gave me is they gave me my delta H. Thank you for that. I appreciate that. Because is that what Mother Nature wants? Does she want to go lower energy or higher energy? Lower, right? So that's a good thing. Now, if I look at it from the standpoint, in this case, my delta S, is my delta S going to be positive or negative? So I'm starting off with something that's aqueous, I get something that's liquid, and I also get something that's a gas. Is this growing in entropy?
Yes.
Absolutely. So I'm going to say, hey, delta S is going to be positive in this case. If you remember, I told you that if you give the universe what it wants, then the universe is going to say, hey, I am thermodynamically favorable, right? And therefore, my delta G, I already know it has to be what? What do we say? If it's favorable, it has to be? Ooh. Negative. And once again, watch that video as well. This is going to tell you in the video. It's going to go over and say, because if you look at delta G, it's delta G equals delta H minus T delta S. Hey, this is going to be a negative value. Minus, temperature is always positive. We said delta S is positive, so this is really like a positive times a negative. That's a negative. Plus a negative, I'm getting a negative out of it. It's going to always, in this case, be negative in that case, under this condition. Which means that when I go look at the answer here, I'm going to find the delta G that's going to be negative, right? And then also find one that has the delta S as being positive. Which means the answer for this problem is going to end up being what? Is it D? I don't even know. I gotta look. Is that the one that gives us negative?
B. Oh. Oops.
It's B, right? Because I see B says delta G is negative, and also delta S is being positive in this case, so it's growing. Let's look at another one here. All right, the reaction represented above goes essentially to completion. The reaction takes place in a rigid vessel. What can we infer about the delta S for this reaction? Let's see. Ooh, whoa. Oh my gosh. That delta H is a positive. Does the universe like that? Absolutely not. But they said that this reaction went to completion, which means that it must be taking place, right? That means my delta G has to be negative. The only way that we said we can have an endothermic process be spontaneous is only if my delta S is going to be what? Remember, the universe does not like this. They're like, delta S must be positive. And if you look at it, this is one of the things I talked about in the video yesterday. And you're going to see it. It's going to say, hey, if this delta H happens to be positive, so say that's positive right there. Remember, I want my delta G to be negative because it's spontaneous. So I know no matter what, this thing better come out to be negative. Watch what's going to happen. You're going to see this in the video when you watch it tomorrow. In the video that I showed you, I just simply said, what if hypothetically I made the delta H 1? Just say that was it. And let's just say that hypothetically I had minus, and I'll make the temperature in this case 1 as well. So I'm going to make the temperature 1. If my delta S is negative as well, so say it was negative 1. Negative times a negative is a positive, plus a positive, that thing is not going to happen. But if you look at it, even if I have something like this right here, say this was 100. No, we'll just say 10. Say it was 10 here. And I went with a temperature that was right here of 1. And I said, hey, in order to force this thing to go, I need my delta S to be plus, we'll just say plus 1, hypothetically, just speaking. Just make it up. Would this thing proceed as written right now? That's going to give me minus 1 plus 10. Is it going to proceed? And the answer is no. That still gives me a positive. But in the video, if you remember, one of the things I even told you yesterday, well, last time we were in the class, I said if delta S was positive, and if delta H was positive as well, then the only way that this thing could actually occur is under increased temperature. You're going to see it in the video. Because if you look at it, if I increase the temperature to maybe, I don't know, 11 right here, 12 right there, 13 right there, so long as I raise the temperature, hey, stranger, how's it going? If I raise that temperature up, then hopefully we're in agreement that this part right here is going to outweigh that part right here. So one of the things you'll see, just watch the video, I'm telling you, it's going to pay dividends, because I show you specific examples of how we can actually force something that even though one of the things says, I don't want to occur, I can still force it so long as I make this. Once again, that needs to be positive, and I just need to raise that temperature to make this component beat out this component sitting over here. Just like in the video, I'm going to tell you also that if I had something like this, delta S equal to negative, delta H equal to negative as well, well, under that scenario, watch what's going to happen. I'm just going to change this thing around. Maybe I'll make this thing right here negative. Where can we go? Negative 10. We'll go negative 10 here. And if I make this one, we'll keep it as 11 here. And I make this one a negative 1 right here for my delta S. Once again, universe is like, I hate this. I don't like that. Oh, I love you. Thank you. But if you look at it, this negative times that negative, that's a positive 11. Minus 10, that gives me a plus 1, doesn't it? But at the same time, if I want this thing to really proceed, why don't I just do something like this right here? Decrease that temperature. Because if I decrease the temperature, then I make this thing become more and more smaller as positive. That's larger as a negative, and it's just going to kick out and make this thing, once again, proceed. In this case, at a low temperature, where if it was at a higher temperature, it's not. Watch the video, just pointing that out. I just want to do a couple more problems, and then we're going to jump ahead here a little bit. What do we got going on with this problem right here? What does it say? The delta G value for the reaction represented above implies that the decomposition is thermodynamically favorable. However, H2 is typically stable up for a year stored in a dark bottle. The best explanation for this is thermodynamically favorable. Blah, 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 blah. Okay.
Did we get an answer for 4?
4, we said the answer was going to end up being, we said, if it's endothermic, that means that my delta S, if it's occurring spontaneously, it implies that my delta S has to be what? And then give me anything here. So what can we infer about the delta S? Delta S must be positive, doesn't it? Because I need it to be positive so it can actually outweigh and beat out the fact that the delta H happens to be positive as well.
So it would be C?
So in this case, it must be positive since delta G is negative and delta H is positive. Absolutely, it's going to be C as being the answer. Everybody okay with that one? All right, going on to number 5. So let's look at 5 really quickly. So for this one, and I want you to see this one because this one is kind of important. It simply says that, hey, you know what? Yeah, we got this thing. It's going to decompose. The exact same reaction. It is going to be that, once again, hydrogen peroxide, decompose it. And it says, hey, you know what? It is thermodynamically favorable. That means that, once again, it's going to go this way. I know automatically in my head, delta G is equal to negative. But they're saying that for some reason, it takes a really, really, really long time for this thing to play out. I don't care. Delta G is still negative. I told you it takes a very, very long time for a diamond to eventually thermodynamically turn into a graphite in this case. If we're dealing with how long it's taking me to have this process play out, I'm really dealing more with what branch of chemistry am I dealing with? How long it's taking for this thing to take place. I'm really talking about what? What am I dealing with? So A, it is only thermodynamically favorable in the presence of a catalyst. B, occurs with an increased entropy because O2 is a product. C, it is reversible. H2O2 is produced almost as fast as it's decomposing. D, has a slow rate at 298 kelvins because the activation energy is relatively high. What's going to be the answer here? So they're saying it's occurring at a very slow rate. I don't know. Which one? That's what I'm going with. Because anytime I'm dealing with the speed at which a reaction is going, thermodynamics just says, hey, it will go. It doesn't tell you how fast. That's kinetics. That's all about kinetics. That's just the fact that it has a really high activation energy barrier that's preventing it from actually going fast. But it will go in this case. For number 6, let's see what's going on here. For this one, they're asking you, hey, delta G, we got 2 molecules here. And this is actually biology. And this is why sometimes biology, they kind of deal with the Gibbs free energy. But if you look at it, it says, hey, 2 molecules such as amino acid and this peptide are joined according to what's above. Thermodynamic data for the reaction are listed in the table below. It says my delta G happens to be this number here, my delta H happens to be positive, and my delta S happens to be, in this case, negative. Which of the following temperature conditions is the reaction thermodynamically favorable? Okay. Well, if I look at it in this case, I think I'm done here. Delta H. How does the universe like that delta H? Is it happy with that? No. Delta S. Is the universe happy with that either?
No.
You're not giving the universe anything it wants. Guess what temperature this thing is going to be thermodynamically favorable at? None. It's not going to happen. If you're not giving the universe anything it wants, it's like, no, thank you. I'm just not going to happen here. Now, if this thing would have been, watch this, say it was positive, and say that was positive there, then I'm going to tell you right now, positive, the way I want to get this thing to actually proceed, I need to do what with the temperature? Increase it or decrease it? Exactly. Positive, increase. Because if you do it, what it's going to do is it's going to cause, once again, that delta G equals delta H minus T delta S. Well, if this is positive, I need, when I add this positive thing here, put that temperature up really high. Give me a nice negative to beat that positive out in this case. But for this one, it's just not going to happen. I'm sorry. You're not giving the universe anything at once. The universe is like, unfortunately, yeah, this is just not going to happen here. All right, a couple more problems, and then we'll talk about what we're dealing with today. Can we do this one here? What's the next one on our list? That was number, what was that, 6? Number 7, can we do this one? You can't do this one yet. You gotta watch the video, because this one is dealing with the equilibrium constant. And one of the things that you can do is you're gonna notice there's an equation up here. And it's kind of really cool. That's one of the things I got excited about in the video yesterday, is you're gonna find out that for any reaction, you can find out what its equilibrium constant is gonna be. There's a really easy calculation you can do. I don't have to take the equilibrium constants for any reaction. I can tell you to go find this delta G. I'll explain how to do that in a video. And once you know that, these two things are just, hey, the temperature at which the equilibrium is taking place, that's the R value, which is 8.314. You'll see in the video as well. Just solve for K, and you can figure out what's going on with the equilibrium. So that one, I can't really go over without you watching the video. So I want to try another one. What we got here? This one looks like it could be fair game. We've got the oxidation of a solid. It's represented by the chemical equation above. Which of the following correctly explains whether or not the reaction is thermodynamically favorable? So they give me my delta H is negative. Thumbs up. Looks good, right? Delta S. Ooh, let me look at that reaction. Is that delta S going to be a positive or a negative?
Negative.
Look at it closely. So we got a solid and a gas, and it's now going all into a solid. So that's going to be what? Negative, right? It's becoming more organized. So even when I look at this, if this was actually on the May exam, I would say, okay, well, guess what? I get to eliminate a couple of problems. You're showing delta S as being greater than 0. That's wrong. You're showing delta S being greater than 0. That's wrong. So it's really between these two right here. And if I have a delta S that is positive, and I got a delta H that is negative, guess what's going to happen with this reaction? Is it thermodynamically favorable? Delta S is positive. Wait. We said delta S is going to be negative. I'm sorry. Delta S is negative. Delta H is negative. If I want this thing to be thermodynamically favorable, what do I need to do with it? Lower the temperature. That's what I'm looking for. I'm lowering the temperature. Because if I lower the temperature, then once again, I'm going to allow this thing to kind of go and get a delta G that's going to be negative.
But if you don't do anything, then it's not thermodynamically.
Well, in this case, I don't know, because I don't know what the actual delta S is going to be in this scenario. Because theoretically, if I look at it, under what we're just talking about right here, I could say that, hey, the delta H, so in this expression, I could say delta H, I'll write it here, delta G equals delta H minus T delta S. So the delta H here is minus 1,650 kilojoules per mole. Minus, well, the temperature sitting right here. Once again, maybe the temperature happens to be 1 Kelvin. Maybe in this case, I have something such as the delta S, because once again, I don't know what the delta S is going to be. Maybe it's 1,700 in this case, kilojoules, mole, times Kelvin. So the Kelvins will cancel out. Under this scenario, I can clearly see that, hey, because you're positive, this is going to be more positive. It's going to outweigh that negative, and we're going to say it's not thermodynamically favorable. But at the same time, what I can see here, oh, actually, this is negative, sorry. Negative, negative, positive, and it's going to make this thing positive. But if I can keep on just taking this temperature and making it lower and lower and lower, then I can force this thing to once again occur. I don't know what this is. That's the problem. They don't tell me what it is. So the only thing I can tell you is that I know for a fact that it will be thermodynamically favorable if I lower the actual temperature in this case. Because as I lower the temperature, I'm making this component, which is going to end up being net positive, but it's just a really small positive value, and allow that negative to outweigh it, and therefore get this thing to actually proceed. All right.
So it's A.
So the answer is going to be, what does it say?
It says thermodynamic.
Yep, that's going to be it. But it's not at any temperature. So once again, if I raise that temperature, it's going to stop it from being thermodynamically favorable because I'm going to end up with a delta G that's going to be positive. All right, what do we got going on here? For this one, it says, we observe a reaction of KCl. Which of the following is true about the thermodynamic capability of the reaction? I'm trying to see what's above. Gotta read the whole thing, that's the problem. All right, so we got the element K and Cl react directly to form KCl. And we get a delta H, which is going to be negative. So if I look at it, look what's going on here. Delta H, we can definitely say is going to be negative, right? Because it shows us it's negative. What's going to happen to the delta S for this one? It's also negative. I'm done in this case. I know what's going to be. I know this thing is going to be thermodynamically favorable only at very low temperatures in this case. That's how kind of the AP is going to treat these sort of multiple choice questions. They're going to go in and try to give you, once again, feed you pieces. It's just up to you to kind of find out what's going on here. So the reaction is unfavorable, it's favorable, driven by blah, blah, blah. What else do we have here? Oh, okay, so if we look at this one, what's the driving force? They didn't even put the temperature in. They told you that in this case that the entropy was going down. And it said the enthalpy is also going down. Who's the driving force? What's responsible for getting this thing to even go in the first place? The enthalpy, exactly. It's not the entropy. The entropy is fighting against Mother Nature. The driving force behind this is the sheer fact that, hey, it's going down lower in energy in this case. So therefore, I can clearly see that, hey, the driving force is going to be, which one is it going to be? The reaction is favorable, driven by the enthalpy change only. That's it. That's the only thing that's kind of driving this thing. Any more problems before we move on here? Ice cube, blah, blah, blah. Now we'll look at it. Might as well. It's an easy one too. I like easy problems. So it says an ice cube, or a cube of ice, is added to some hot water and an insulated cup, which is sealed. There is no heat exchange with the surrounding. What happens to the total amount of entropy when the system reaches equilibrium in this case? So think about it. It's an ice cube. I'm putting in warm water. The entropy, is it going to grow, decrease, or remain the same? Grow. It's going to grow. So I know entropy better grow. And if I look at the actual energy, what happens to, what does it say? What happens to the total energy in this case? the total energy is, guess what, gonna be? It's gonna be constant. It didn't say, now we said what happens to the water, the energy of the liquid water. Then I can talk about, or if I said what happened to the energy of the ice cube. But total, the energy that was lost by one is the energy that's being gained by the other. So therefore, it's gonna end up remaining constant in this case. Come on, I've got some easier ones in here. Oh, this is easy, I love these. These are great. Let's look at this one really quick. Then after this, I am gonna get started with the next chapter. And the next chapter we're gonna get started with, it's just gonna be a review. There's things that we've already seen in this case. So if we look at it, before heating, after heating. Okay, I see it. So if we look at it, the question they have here is they simply go in and they're talking about the particle diagram represents the change in physical states that occur after heating two separate solid substances. Which of the following best explains what's going on with the actual delta S's? I am so done here. Who has a greater delta S? Is it going to be 1 or 2? 2. So therefore, I'm done. The answer has to be what? C. Once again, some of these problems are really, they're just that straightforward and not difficult. This is a delta G that's dealing with, I think, equilibrium, is it? Following justifies the fact that, yeah, you need to do that equilibrium constant. Anything else here? I can go there, you can do that yourself. We'll look at this one, and then I'm done. After this one, I'm done. Man, I love these problems. All right, if you look at this thing, they're showing you this reaction here. And they're showing me that this reaction happens to be, is that an endothermic or exothermic enthalpy diagram?
Endo. Because it's...
Which one is it going to be? Endo, right? Isn't it going higher in energy, starting lower energy, and then the products are up here higher energy? It's endothermic. And the question is, hey, this reaction is thermodynamically favorable under the conditions of 298 kelvins. Therefore, the delta S must be what? Positive or negative?
Positive.
It has to be positive. Because see, remember, in this case, if you are going to end up, in this case, being something that Mother Nature does not want, you're going higher in energy. Mother Nature's like, oh, I don't like that. That is awful. You can't do that. At least give me something. Well, it's not going to give you. It's going to give you disorder in this case. That's the only way that this thing can be thermodynamically favorable. I can't give it the other thing because then it gets neither one. So for this one, if I look at it, the answer is going to end up being that the delta S is going to be less than equal to delta H greater than delta H. It's going to be less than, in this case, the delta H at 298 kelvins.
What exactly does delta H mean?
Remember, delta H is a change in energy. So that's all we're looking at. Hey, the reactant had a certain amount of energy, and now it has some new energy. What's the final minus the initial? And then once again, the final would be that energy there, initial would be this right here, and that's just the change in energy that the actual reactant went up to as it went to produce the products here.
So it would be 50?
It would be 50 would be the delta H, exactly. That's exactly correct. How many did we knock out there? We did 13. Do this last one, then we'll be fine. All right, so if you look at this, it says it's an exothermic reaction, right? So it says, hey, the dimerization of NO2 is an exothermic process, represented by the equation above. The forward reaction is thermodynamically favorable at which of the following temperatures? So if I look at it, it's exothermic. What's my delta H in this case? Negative. Okay, so I know that part.
Okay.
Delta H happens to be negative. All right, my delta S, based upon looking at this reaction, is going to end up being what?
Negative.
Positive or negative? It's negative as well. At what temperature is this thing going to take place? Right? Low temperature only. So are we okay with this here?
Yeah.
Okay. So let's get, I need that temperature to be low because as I lower, oh, I should have done an S there.
Because that's not.
Because when you go delta G equals delta H minus T delta S, once again, this negative sitting here times that negative, all of this is going to give me a positive. So that's going to give me net positive. I need this thing to be a really small net positive, and the only way I can drive that positive down is to drive that temperature down in this case. Yes?
Okay, I know this is an equilibrium, so wouldn't it be going both ways? And like, we're applying this to only the
No, okay, but what they're saying, I understand what you're saying, because technically they are showing that equilibrium
Right.
here. But they're saying it's thermodynamically favorable under, in this case, what they got? I know exactly what you're saying. So basically, even with the equilibrium, like when we see equilibriums, and I think I might have touched on this yesterday in that video, if I have A going to B, and say this thing happens to be exothermic, right? And it's in equilibrium. So long as I keep the temperature the same, it's going to be in equilibrium, right? But as soon as I do something such as, hey, maybe I lower the temperature, then it's thermodynamically favorable going in the forward direction in this case. And that's what they're trying to allude to here. They're just simply saying that at whatever temperature, we want to make this thing proceed in the forward direction. What could we possibly do in this case to achieve that? And in that case, if I lower the temperature, then I can get this thing to actually proceed in the forward direction in this case. All right, I don't have enough time to actually do any notes, so I'm going to keep on going on. We have knocked out almost half of the problems here. This one's 16, that's the equilibrium constant. We can't do that. So let's look at this one right here. Ooh, what is going on? I don't know what's going on here. So let's take a look at it. First thing I have here is I've got diagram 1, I got diagram 2. I have no idea what diagram 1 and diagram 2 is referring to, but we're going to figure this thing out together. What I do see is for this reaction, universe is like, yes. Universe is also like, yes as well. You're giving me two great things here. You're giving me this order, because once again, that's a liquid, 3 moles of gas, and now I got a grand total of 5 moles of gas. It's growing in entropy. When I look at the actual delta H, once again, it's going lower in energy. So I can tell you that both of these diagrams seem to kind of go along with that. But I do see there's a difference in that activation energy barrier. So I want to see what this question is. So it says the combustion of this substance is represented by the equation above. And the standard entropy and enthalpy change of the reactions are provided. When the reaction is at 25 degrees Celsius, essentially, no CO2 or H2O is being produced after a few hours. Which of the following diagrams above could help explain the low yield of the reaction under these conditions? So I'm getting a low yield. I'm just not getting as much of the product as I want. It's just going really slow in a sense here. Based upon that information, I'm hoping that we can deduce that clearly it's gotta be diagram number 1 as being the right answer that's gonna slow this thing down, right? No, I see a head shaking like absolutely not. It's gotta be diagram 2, right? Because that has a much larger activation energy barrier, which means it's gonna take more energy to get that thing to go. Like this one's like, thank you, I'm going. Anything above that, I'm going. This one's like, yeah, I'm not doing it. You don't have enough energy in this case. So for this one, I can clearly see that it's gonna have to be diagram number 2. That's the explanation for why this thing is actually proceeding at a much slower rate in this case. So between C and D, let's see, diagram 2, because it represents a reaction with a higher activation energy barrier for the molecules to overcome and very slow reaction rate, even if it is thermodynamically favorable, which we said it was gonna be in this case. So I believe the answer is gonna be C. We've got 5 more minutes here. Number 18, you're gonna have to watch the video to understand that one. Number 19, same thing, watch the video. Number 20, you're gonna do this one, and I'm not gonna do 20. Look at it and tell me what the answer is gonna be for number 20. So you might have to open up the worksheet so you can kind of see the answers that are going on down there. Is everybody finished? I don't know. I didn't really look at the question and answer. I can kind of get a sense of where they're going with. Clearly, I see more over here, few over there. The answer's gonna be what for this one? What is it? I don't know. We'll find out. I can tell you for one thing, it's negative, isn't it? So it's got to be between A and B, and you're saying B. Delta S is negative because the number of molecules of gas is decreasing. I'm going with that as well. I'm done. B is going to be the right answer. Try number 21.
Wait, sorry, 20 was B.
20 was B, yeah. Wait, let me shoot. Do 21. You might not be able to do 21 because they gave you equilibrium constant there, didn't they? They did. You can't do 21. 21, you have to wait. I'm sorry. I didn't realize they were giving you equilibrium there. 22, you definitely can do that. 22. When water is added, reaction occurs. Which of the following statement about thermodynamic favorability of this reaction at 298 kelvins? What do they give me here? I'm so done. They gave me my delta H, they gave me my delta S. I know, like, that's the nice thing about these is I already read the question, but I already know where they're going with this one. Everybody finished with this one? If it's going to be thermodynamically favorable, it's only going to take place. I don't even know what the question or the answers are, but I bet you it better say something about at a low temperature or something like that lines. Is that what it says?
Says it's driven by.
Oh, so look at it, which one's driving? So clearly, the one that has to be driving this thing is going to be the one that's going to be which one of the two?
H.
Delta H, clearly. Because this is, once again, going against what Mother Nature wants. This is giving Mother Nature what she wants. So therefore, the change in the enthalpy has to be the driving force behind this one. So we did quite a few of these problems here. What you are going to do is you are going to try to finish, well, you're not going to try. You're going to finish at the multiple choice portion. And then you're going to notice that there is some free response questions after it. I want you to do multiple choice, so that I want to be finished by Monday. So Monday, the day after Fun Day. The free response, that is going to be due on Tuesday, the day after Monday. On Monday, what we're going to do is we're going to start with that new last chapter. We're going to try to spend about maybe 3 days, hopefully max, and we can hopefully be done with that chapter. The key is, once again, make sure you're kind of comfortable with this sort of concept. These questions are easy. They're not